Hi there. On the bench, I've got a Kenwood TL-922A RF power amplifier. It has two 3500Zs inside of it and does 2 kilowatts PEP input, so it makes quite a bit of power. And this is hooked up to 220. I have a 220 circuit on the bench here. So this is just going to be a quick video because I'm in the middle of working on another video right now that's been taking a long time to do, and my friend that owns this amplifier here would like to have his amplifier back, and I'd have to push this off a ways in order to continue with that other video. So I popped this up on the bench in the meanwhile, and I figure it would be probably beneficial to a lot of people to show one of the modifications that's necessary to run this amplifier with a solid state radio, a newer modern transceiver like my ICOM back here. If you own one of these things and you've hooked it up to a modern transceiver, you'll know what I'm talking about with the keying circuit. And if you haven't, well, you're probably really lucky that you stumbled across this video, because if you don't do this modifications, you are going to have problems with your transceiver if you hook this TL922 up to it. And I'll explain why here shortly. Now, I've also done some modifications to the biasing circuit in this thing, and I'll illustrate those here quite shortly. And I'll just go through really quickly and give you an idea of some of the sore spots in this amplifier that you can address while you have it open. Now, keep in mind, if you're going to work on one of these amplifiers, this thing has over 3,000 volts present inside it when it's hooked up to the line. When I say hook up to the line, that's 110 or 220. Whenever it's plugged in, there's 3,000 volts present inside this amplifier. If the bleeder resistors on the capacitors are open, it will hold that voltage for a very long time, and if you come across it, you're dead. Okay, there's an incredible amount of current behind this 3,000 volts. It's not like, the old television sets that had really high kilovolts but very low current. There is a lot of current inside these amplifiers. So you never, ever want to come across that 3,000 volt supply, or anything in this amplifier for that matter, because there's high voltage present everywhere. All the taps on the bottoms of the transformers here are all open, and there's 220 or 110 present on that if it's plugged in, or anything like that. So you got to be very careful, and there's a lot of shorting bars inside of this amplifier so that if you remove lids, it'll short out the high voltage power supply. So there's a lot of safety things in here to keep you from hurting yourself. If you are not familiar with these amplifiers, do not even attempt to go inside this amplifier. If you're going to follow along with me and try and learn about this amplifier, if you're going to work on one of these things yourself, you're doing so at your own risk 100%. These things are dangerous. You got to be very careful. This isn't a standard vacuum tube amplifier. This has got incredibly high voltages present inside of it. And all vacuum tube RF amplifiers are the same thing. So if you're going to follow along with me, you got to know what you're doing. You have to take caution, and you're doing this at your own risk. Okay, let's get into this thing, and I'll show you exactly what I've done, and we'll get on with the show. Here we are in the bottom half of this Kenwood TL-922A RF power amplifier. Now, some of the problems that I encountered with this amplifier, well, the first problem that I encountered was the conductivity in the contacts of this relay just below this choke here. The contacts were so incredibly tarnished or blackened that no RF power was getting through it. So what I had to do is remove this relay and of course polish the contacts up. So getting this relay out of here just below this choke is quite a job. You need to go in through the top and remove a bunch of Phillips screws. You have to make sure that this plate capacitor here is completely meshed so you can get your screwdriver in there. And of course you have to unsolder all the coaxes off this relay and the coil wires, and you also have to remove this choke. And this also connects to this box here where the RF runs into this tuned circuit here. So you have to unsolder all that, and then of course this comes out. You got to wiggle it out, move the coaxes out of the way. You'll probably have to remove the zap straps. You'll have to put on new zap straps later on. And get this relay out of here. Now there's one screw right in the center of this relay that basically disassembles the entire relay. So there's a spring across the moving aperture that you can very easily remove with your finger that just holds the moving aperture into the relay itself. But that one screw basically removes everything altogether, so it's kind of put together in layers. So now when you take that screw out to get at the contacts, you got to be very careful that you don't lose a very small spring that's in a cup inside here. It's about, a centimeter long by about half a centimeter in diameter, and that thing's going to go doing and end up somewhere in your carpet if you're not careful. So you got to be very, very cautious when you remove that. So remove that slowly. Now when you get the relay apart, if your relay does have problems, you don't want to sand or you know, burnish the contacts in any way, shape, or form. You don't want to take that silver plating off the contacts of this relay. What you want to do is get silver polish and try that first and see if they're actually pitted. Now, these looked horribly pitted to my eye when I took it apart, but I tried the silver polish, and actually the silver is just fine. So what I did is the product called Wendell, it comes in a pink can. It has a bit of an ammonia smell to it, but it works extremely well. You know, put it on the contacts and let it sit for about 5 minutes. Just sit there, little dots of Wendell on all the little contacts. And then I got a polishing rag, and I just worked at the contact, kind of put the polishing rag on there and just worked at the contacts like this. And they look like chrome now. And there's really good continuity between all the contacts in that relay. So that's one thing to do. So always try to polish the contacts first before you try and burnish or sand them, because if you sand them, you'll take the finish off, and then the relay will fail in short order. So you don't want to do that. So I got that all back together and put this back in, and now that particular part works. Another sore spot in this amplifier was the bias section. Now there was some flashover happening in here, and of course that causes this Zener diode that sits in here to deal with some very heavy current bursts, and that opened the Zener diode. And of course the Zener diode was open, and because the Zener diode was open, there's a capacitor that's across here that exploded. The top blew out of it. And because the voltage goes high across this little electrolytic capacitor here, it's 100 mics at 16 volts is what this is supposed to be. So if the Zener's working, of course, it's not going to go above 7.5 is the factory rating. So I designed another circuit, a resistive bias circuit under here using a MOSFET and some stuff that is extremely resilient. If this thing has flashover or anything, this will put up with it. And so you don't have to really, it makes it really resilient to any kind of abuse is really what it is. This thing will just hang in here through all the tough spots. And I'll illustrate this little circuit on the whiteboard here quite shortly, and show you how to make one if you want to build one yourself for your Kenwood TL-922A. Now this is a capacitor down here that was leaking also. This is the 116 volt DC supply, at least that's what it measures at the relays. This capacitor was leaking, so I replaced it. And I put a 450 volt rated capacitor in there, so that's going to hang in there through tough times also. I also designed a circuit for this to interface this with a modern transceiver, because the 116 volt relay keying in here will absolutely weld contacts together inside of a modern transceiver, especially if you have a reed relay inside it or something like that. So I designed a small little circuit that's very simple to put together that may benefit you and it may not benefit you, and I'll explain that at the whiteboard too. So I found that really odd why they did that with this amplifier. You know, they could have used 12 volt relays or something like that, and they didn't need to run you know, 100 well, I think 116 is what it was measured at the jack running out of this thing. 116 volts DC at 33 milliamps. So that creates quite a spark when you short that RCA plug in the back, and of course that welds contacts in any small relay or a reed relay for sure. So hopefully, as mentioned before, you're seeing this before this has actually happened to you. So this is pretty much what I've done. Of course, you know, part of the cleaning procedure, you de-dust the whole thing, you know, wipe all the dust out, because that causes flashover within itself. I cleaned the switches, all the contacts in the rotary switches here. And, you know, just basic routine maintenance after that. And, you know, remove the tubes and check the parasitic traps on the top. And I'll talk to you about the parasitic traps a little later on in the video. And, you know, went in and cleaned the fan and on the whole upper side. We'll view the upper side in just a little bit here. So what I'll do now is I'll show you the bottom side of this FET here, and then we'll head on over to the whiteboard and I'll show you how the circuitry is put together for both the relay saver and the biasing circuit here for the 922A. This is the heat sink that the original stud mount Zener diode was fastened to for biasing the 3500Zs. So you can see the hole here where the stud came through. That's now used for running the wires through to the new FET that's mounted on the other side. And the wires, of course, just solder right to the legs of the FET there. So that's what it looks like. Now let's head on over to the whiteboard and I'll explain what all these parts are for. These are the two circuits I was telling you about at the bench. This is the new biasing circuit for the Kenwood TL-922A, and this circuit here is the keyline interface. And we'll talk about this circuit first and what it does. So the Kenwood TL-922A has 116 volts DC present on the relay jack that tells the amplifier when to turn on. So basically your transceiver shorts that to ground and it puts the amplifier into transmit mode. Now 116 volts DC at 33 milliamps, if you put a current meter in line with that jack and short it to ground, it's 33 milliamps at 116 volts. That's a lot of current, and that welds relay contacts together inside solid-state transceivers like my ICOM IC746 or 756 or any modern transceiver with a small relay in it. And what this switching network here does is it acts as an intermediate switch between the transceiver and the Kenwood TL-922A, and this is what switches the current to ground. So your modern transceiver will only switch 470 microamps to ground instead of switching 33 milliamps, and that's quite a difference. There is no spark or anything present at that when you short that out, whereas at 33 milliamps and 160 volts you get quite a nasty little spark that welds contacts together. Now keep in mind that this isn't a solution for all transceivers. Some transceivers have bipolar transistors in their switching section or a MOSFET, and they use that to tell an amplifier to turn on or off. So basically they're using a transistor to switch the relays in an amplifier on or off, and instead of using a relay to turn relays on and off. So you got to be very careful, because 106 volts might exceed the breakdown voltage of the transistors in the keying section or the relay switching section inside your transceiver. So you need to check your service manual or know just a little bit about your transceiver before you proceed with hooking this amplifier up to really to anything. So for most transceivers this will work, but for some it won't. So for my ICOM IC746 this definitely works, and it'll save my my little reed relay from welding together. So how this circuit works is this goes off to the amplifier. So there's 116 volts at 33 milliamps here waiting to get switched to ground. This little MPSA92 PNP transistor does that switching. Now the MPSA92 is a little TO92 package transistor rated at 300 volts, and it can deal with quite a bit of current too, so it has no problems turning the relays on inside this amplifier. Now what happens is obviously the voltage is waiting here to get turned on, so when we ground this port out up here, this is the one that runs off to your transceiver. So when you grab the microphone and squeeze the push to talk switch on your microphone, there's a little relay that closes in the back of your transceiver, and that relay, when it closes, tells the amplifier to turn on. Okay, so when that closes, that just connects this to ground here, and when it connects that little jack to ground is when it turns this transistor on. Now the resistors in this circuit are all kind of, I would say, very generic. You could move them around a little bit and you'd still have really good results. This isn't a finicky circuit at all. You could put a 220 ohm resistor in there. You'd up this to over a milliamp if you did that. Or you can take this 4.7K resistor and change it to a 47K resistor, and it'll still key the relays in or turn the relays on just fine. So this 4.7K resistor is just chosen because it doesn't run this transistor so hard into the linear region. Now this transistor right now is still running in the linear region just a little bit, and that's absolutely fine because the current specs on this transistor deal with those relays with ease. Absolutely no problem there whatsoever. It doesn't get warm or anything. So this diode here is acting as a snubber to just suppress any inductive spikes that may be present at this point here. This 0.01 mic capacitor has to be rated at 150 volts, and that's there just to pull RF off the diode and keep RF out of the circuit. There's another capacitor 0.01 at 150 at the base of this transistor here, and that's to keep RF off of it. This 100K was just placed in here to help the ease of the recharging of this 0.01 mic capacitor. You can probably get away without using that, but it doesn't hurt to add it in there. This way you're not using the current path of the transistor to charge that 0.01. You're using the resistor a little bit more to do that. So it just eases things up on the transistor a little bit. You got to take care of these little guys. They're pretty frail, you know. So now that's pretty much this little circuit here and how it works. This could be built into a little plastic box and placed in line, so you'd run an RCA cable into the box and then that would run out to your transceiver, and that would save the contacts inside your solid state transceivers relays. Now if you're looking at this video because you've already welded the contacts together inside the relay of your transceiver, there still may be some hope. What you got to do is open the transceiver up and get a piece of plastic like this, or a small wooden rod, and put it on the corner of the relay and get a little rubber handled screwdriver and just knock the corner of the relay while using an ohm meter to see the contacts, to read the contact resistance. So if you have no power hooked to your radio and the relay is welded shut, when you hook an ohm meter to it, it'll read low ohms, or you'll get a continuity tone or a beep at that point. So if you put a rod at the end of the relay and knock on it gently a few times, maybe move it to the other corner and knock on it many times, more times than not, it will free that little contact up, and then of course your continuity beeper will stop and you'll see the ohms go high. And that may help you out. Now, when I talk about knocking on the corner of a dowel or a piece of plastic, I'm not talking rapping on it so you're ripping the relay off the board or destroying the relay. You need to use common sense when you're doing this. So just do it very, very carefully on each corner, and you give it a shot. If you have a transistor that's shorted, putting a rod on the transistor and knocking it will not work as well. So that's pretty much done there. So let's talk about the bias circuit here and how that works, okay? So what I've done is I've replaced that Zener diode with a very large MOSFET transistor, and this is just resistive biasing here is what this is, a resistive bias network. And it works very, very well. So what was happening in this amplifier is there's a little bit of flashover, and the flashover, of course, causes heavy current draw, and that absolutely destroys that Zener diode. So this is a very, very tough MOSFET. It's an APT5022 BNFR, and it will deal with flashover just fine. So this will live through flashover moments, and you'll still be able to use your amplifier without having to go in there and change Zener diodes or small little dinky TO220 style transistors. So this is a TO247AC, I believe it is, if I remember correctly, package transistor. And it deals with some pretty big current and some pretty big voltage. You can look up the specs. So I've got a bunch of rails of these things full, so I just pulled one out and used one of these things, and it works really good. The voltage is still above the gate threshold, and it turns it on really quite well. So this is actually running in the linear region. Of course, to control the bias, it has to run in the linear region. And it's so big that it, at full power, 1.1 kilowatts out into 50 ohms, so it's pulling 550 milliamps, or no, is it 520 milliamps? The transistor about 20 seconds into holding the key on at that point, the transistor starts to get a little bit warm, or I should say the MOSFET starts to get a little bit warm at that point. So that's why it's attached to that heat sink. But still, this thing is running in the linear region, and of course that's why it's acting as kind of like a variable resistor at this point. So now what's happening is this here is controlling this. This is turning the gate on and of course keeping it in the linear region. This little Zener diode here is just to protect the gate from any kind of spikes or anything that may happen. So if you did have an inductive surge or something like that, it surged really hard here, really fast, this would suppress that to protect the gate from getting zapped. It's just a 15 volt Zener. It's a 1N5245. This is a 4.7K resistor here just to hold the gate down. Now there's a 180 ohm resistor here just to act as softening for the gate. If you want to change the bias point in your amplifier, if you're running a bunch of 3500Zs and you want to use this, all you have to do is add more diodes to lower the current, or remove diodes to add current at this point. Now, of course, this amplifier is running a little bit over 3 kV, so if you have 3500Zs running a little bit higher, you may have to add more diodes to get the same kind of currents that I have present here. And of course, if you're running lower, things will change yet again. So these are the results that I have here. The idle current in SSB mode is 165 milliamps, and in CW it's 95. Now in the manual they say they want it to run around 200 and about 100 for CW. Now I find 200 kind of hot for these tubes. If you just apply the relays inside the radio, so basically it's connecting the cathodes to this circuit here. You notice after about 15 or 20 seconds you'll start to get a red glow to an orange glow on the plates of the 3500Zs. So by lowering the current, they will run really quite satisfactorily, right down to about 160 milliamps, and they run really well at that. So instead of causing these tubes to run so hot, I've just lowered that current down to about 165 milliamps. Now one tube is a little bit stronger than the other two, which is another reason I did this, is because one tube will come in a red just a little bit quicker than the other one will. So the tubes are, relatively don't have that much time on them, but they are a little bit different. So this also helps out with that, since one wants to current hog just a little bit. Now, another reason for running this a little bit cooler in this TL-922A is because the cooling system in it really sucks. It's just the truth. It's a really bad cooling system. It has a computer fan on the back of it, and it just draws air past the 3500Zs kind of in a real gentle manner. 3500Zs should be forced air cooled no matter what kind of design they're in. Anything where a plate aperture that's incredibly thick, made out of graphite, that can glow orange hot, is gonna, cause an issue with seals eventually. And of course, any kind of amplifier that isn't blower cooled, it doesn't have any kind of chimney around the 3500Z, you're risking, if you're using this thing for any kind of mode that's other than CW or SSB, if you want to use it for any kind of AM use, or any kind of mode where that it's going to be, drawing any kind of current, those tubes are going to really get hot. And that fan that they've added there, or the fan that they have in the back, really, it's just, it's pulling a breeze past those tubes. They really need to be forced air cooled. So by running the idle current down a little bit more, again, just keeps the tubes a little bit cooler. Now, for those of you that don't realize it, the plates in these power tubes are supposed to glow red to orange when they're in service. And like if you have a 6L6 in a normal guitar amplifier or anything like that, they're not supposed to glow red at all. But in these tubes, that's how these tubes getter. 3500Z tubes getter themselves by having the plates glow orange to red. In some tubes, like 4-1000s, the really large power tubes, they can glow white inside. Those plates will get that incredibly hot, and that getters the tube at the same time, but they really, really need to be forced air cooled when they're running like that. Or what happens is the glass seal around the pins in the base of the tube, they open up and they draw air in, and of course the tube goes faulty. So in order for these power tubes to getter themselves, they do need to glow orange a little bit in order to absorb the impurities within the glass bulb. And of course, because everything is off-gassing in there still, so this just helps clean up what's inside that bulb. So if your tubes run too cool all the time, you could run into issues again. So a little bit of orange in the plates and some 3500Zs never hurt anything. Again, they just have to be cooled properly. So with this Kenwood TL-922, it really is a fine balance between the cooling and where you want those tubes to run. And of course, there was a lot of that thought in designing this circuit also. So the regulation, I should say, or how it holds the cathodes, is actually pretty well. 165 milliamps is the idle current, and it sits 4 volts at this point here. Now, at full power, 1.1 kilowatts into a dummy load, it goes to 4.2 volts, and that's the only movement there. So it's actually working really well. So the FET works very well in this condition, and as I say, it's pretty robust. If you get any flashover, the chances are this FET is going to live through it, whereas if you have the Zener, it's dead like that. So this is the circuit here, and that's how it operates. This capacitor here, if that Zener diode goes open, this explodes and blows its innards all over the inside of your amplifier. You'll find that little capacitor, that little one that I pointed to, it usually faces up against the chassis. If your Zener's gone open and it hasn't exploded, just bend that capacitor down and look at the cross on the top, the little vent, and chances are it has burst and let the pressure out. Because I believe the factory capacitor was only rated at 16 volts at 100 mics. So I replaced this with a 25 volt capacitor. That still doesn't matter. If this FET goes open, that capacitor will pop too. So you want to check that capacitor all the time when you're working on the biasing circuit, because this capacitor is of course a weak point if that Zener diode goes open. For those of you that are interested in what the inside of a Kenwood TL-922A looks like, this is pretty much it. So the 2 large power tubes fit here, and these are the 2 tubes right here. They still have their parasitic traps on them. So these are them right here, 3-500Zs or 8802s. And these tubes are very strong still. There is absolutely no problem with them. And I've left the parasitic traps on them. Now, when you're tightening the screw up on this, if you're replacing your tubes, if you're tightening the screw up on the plate cap here, you got to be very careful not to over tighten it, because if so, you'll crack this seal under here, and that's the last thing you want to do to your new tubes. So you just want to very gently snug that screw up. And if you find that the old ones are really tight, what you want to do is remove the tube and put your tube, say, on a piece of carpet, and hold this here with a plier. Hold this with a plier, and then don't touch the tube whatsoever, so there's no torsion or torque on the tube whatsoever. Hold this and then undo the screw while you're holding just this. So all the torsion and the torque are on this, and this tube is just floating in midair. Don't ever hold the tube and try and twist on this, or you'll break this upper seal. So that's one trick in order to get these seized caps off the top, or if somebody's used a torque wrench at 100 foot-pounds or something to tighten the thing on. I've come across some of these tubes where these plate caps have just are on so incredibly tight, it's ridiculous. They just have to be snugged, and then just a little bit of tightness, but not enough to wreck this seal up at the top of the tube. Now you'll notice the fan cooling in this is really just a computer fan in the back, and it blows over the glass case of the tubes, and even, well, actually it draws air out the back, but even this little screen here is kind of obstructive to the airflow just a little bit. They're doing this, of course, to keep RF from coming out of the back of the unit. Now, these tubes are actually designed to sit in a socket and have air blow past the pins, and in this little area, and then they have chimneys around them, and air blows past this entire tube, and it cools this upper seal on the top and here. So really, if you think about it, these tubes aren't getting cooled as well as they could be getting cooled. So, of course, the best way to run a tube like this is to have it blower cooled, and that way you don't have to worry about the glass to metal seal in the base going bad, or the glass to metal seal at the top of the tube where the plate cap is going bad. So these are still relatively new tubes, and they've got lots of emission. This is a graphite plate tube here. You usually tell the graphite plates because they look big and chunky inside, whereas they're just a standard plate, non-graphite 3-500Zs usually have that kind of an oil filter-like looking design inside. They've got those just very thin plate aperture, and once you draw current, they glow red very, very quickly. So these ones here are quite a bit more robust, these 3-500Z. So if you ever replace the 3-500s in your amplifier, it's always good to go with the Z. The Z just indicates that it's a graphite plate tube. So these will comfortably plug back down inside here. This is the left side tube, so this one is going to go in here like so, and then the other tube will go in there. You can see they even mark left and right on the parasitic trap. There's two resistors within this parasitic trap. You also want to make sure that they're good and they haven't split or anything. If those resistors are bad, you'll notice that you have a little bit of reduction in output power, and of course there is more tendency for these things to parasitic oscillate. So you want to make sure that the parasitic traps are okay. And it's pretty much just an overall view of the amplifier. This is the main transformer that creates all the high voltage for this section here, and it's just parts and pieces everywhere. I can sit here and explain it. The high voltage capacitor stack down here, and more relays. This thing's got relays all over the place, and doorknob capacitors, and all the coils it takes to make this thing tune to all the different various bands. So that's what a Kenwood TL-922A looks like inside. I hope you enjoyed this short video on the Kenwood TL-922A RF power amplifier. I really had no intention of doing this video, but when I found out that relay jack had 115 volts DC on it, I figured I'd better show people this modification, so hopefully it saves you from harming your transceiver. So if you found this useful, or you built the project, please let me know in the comments below, and stick around. I'll have more videos like this coming in the near future. So now I'm going to take this thing off the bench and put the other project back on the bench. That's the reason that there's been such a lag time between my two videos here, is because I've been really working hard on that other video. So I'm going to get that back on the bench here, and hopefully I'll be done with that in short order. I don't know, it's been taking me this long so far, so hopefully it goes a little bit quicker. So if you like what you see, give it a big thumbs up and hang around. There'll be more videos just like this in the near future. Take care. Bye for now.